Given question, derive an expression for damped natural frequency of vibration for the system shown in the diagram. The weightless rigid rod is pivoted at point O.
We have to find out the differential equation of motion for this given system. Let us understand the diagram. Mass m is pivoted about point O and its distance from O is 2a. The distance in between this mass and the damper with damping coefficient C is given A, and the distance in between this damper and spring with stiffness K is given A. Now we have to find out the equation of motion. We will consider this mass m is getting displaced through an angle theta about this point O. So we will show this with the help of diagram. So here is the angular displacement we will show about this point O, because this mass m is pivoted about point O. So this is the original position of mass m, and here we will show the final position of the mass m. So here is the angular displacement theta. Now in the direction of the angular displacement, accelerating torque develops, and this accelerating torque, that is, we will show the direction of the accelerating torque because this theta is in this anti-clockwise direction, I theta double dot, where I is the mass moment of inertia for this mass m and theta double dot is the angular acceleration. Now because of the linear displacement of this mass m, so I will show here the linear displacement of this mass m. So here is the linear displacement of this mass m. So what is the direction for this linear displacement of the mass m? That is in the upward direction, because this is the original position and this is the final position of this mass m. So because of the linear displacement of the mass m, this dashpot and spring are also getting displaced. Now we will show it's a displacement. So I will show here the displacement of this dashpot and displacement of this spring. So we will consider this distance for the spring will x and this distance for the dashpot will y, because both the distance are different. So from the diagram we come to know that the displacement of k, that is the displacement of the spring, and displacement of this dashpot, both the lengths are different. Now we know that as the mass m is getting displaced in upward direction, then in the direction opposite to this spring force and damper force will act. So we have to show the damper force Fd in the downward direction, and in the same way spring force Fs will also act in the downward direction. Now if we observe this diagram, here is the accelerating couple I theta double dot, and that will act in the anti-clockwise direction about point O. And here the external torque are due to the external forces. Now which are those external forces? That is this Fd and Fs. So how we can find out the external couple? So if I move the compass about point O in the direction of Fd, then here is the external couple due to Fd. So how to find out the value of couple? So this force multiplied by the perpendicular distance from O. So for Fd, that is for this damper, if we observe perpendicular distance from O is 2a plus a, that is 3a. So we can say that for Fd, couple is Fd multiplied by 3a, and this couple will act in the clockwise direction. Now in the same way we will find out the external couple due to force Fs. So if I move the compass in the direction of Fs, then it is also in clockwise direction. And how to find out the value of couple? This force Fs multiplied by perpendicular distance. So 2a plus a plus a, that is 4a. So I will write here Fs into 4a. Now this accelerating torque, if I give here the negative sign, then these two couples are in opposite direction. So we have to consider here the positive sign. Now what is this damping force Fd? So we know that damping force Fd, that is nothing but this damping coefficient multiplied by this distance displaced, that is we have to take its a velocity. So if displacement is y, then what is the velocity? It is y dot. So how we can define this Fd? So Fd is equal to this damping coefficient c multiplied by velocity. So velocity here, displacement is given as per the diagram we have considered y. So we have to consider here as a y dot. Now what about the spring force Fs? So Fs is equal to spring stiffness K multiplied by displacement. So for this K, displacement is x. So K into x. Now we will find out the value of x and value of y dot in terms of theta. So we will observe this diagram. So I will give here the notation. So here is A, then I will consider this point B, B dash, and here I will consider D, D dash. Now from this diagram we can say that y is equal to this 3a, because O to B distance is 3a, 3a into theta. Because if we observe this triangle OBB dash, then this y is equal to 3a into theta, and therefore y dot is equal to 3a into theta dot. So from this only we have to find out. And what about x? So from this diagram, that is ODD dash, x is equal to this 4a into theta. So we will get the relation in between x and theta, and in the same way y dot and theta dot. So we can replace here x and y dot in terms of theta. So how we can write Fs? So Fs is equal to k into 4a theta, and Fd is equal to, instead of y dot we will write this c into 3a theta dot. So these two are important. Now we know the couple. So instead of Fd and Fs, we will put the value in terms of theta. Now we will apply the Newton's second law of motion. Accelerating couple is equal to summation of external couple. So minus I theta double dot is equal to Fd into 3a plus Fs into 4a, that I have shown here. So now put the value of Fd and Fs. So when we put the value of Fd and Fs, then we will put the final values, that is minus I theta double dot is equal to 9a square c theta dot plus 16a square k theta. Now what is the value of I? So I is due to this mass, and this mass is small, so this I is equal to, that is mass moment of inertia is equal to m into L square, that is this perpendicular distance from this point O. So we know that m into L square, but what is the value of L? L is equal to 2a. So we can write here m into 2a bracket square, that is 4ma square. So we have to take 4ma square theta double dot plus 9a square c theta dot plus 16a square k theta is equal to 0. Now if we observe a square is common, so if we take this common term and move towards the right hand side, then this a square is getting cancelled. So what is the simplified form? 4m theta double dot plus 9c theta dot plus 16k theta is equal to 0. So we can say that this is the differential equation of motion for the given system. To find out the equation for the damped frequency for this system, we will compare the equation of motion for the system with fundamental equation of motion for the damped free vibration. Now if we observe the equation for this system, then it is in terms of theta. So we have to take the fundamental equation of motion for the torsional system, because this torsional system equation is also in terms of theta. So what is this fundamental equation? That is I theta double dot plus ct theta dot plus kt theta is equal to 0. So if we compare these two equations, both are equivalent to each other. Now we will compare the coefficient of theta double dot. So we will say that I is equal to 4m. Then if we compare coefficient of theta dot, then we can say that ct is equal to 9c. And if we compare the coefficient of theta, then we can say that kt is equal to 16k. Now we will find out the value of omega n. So omega n is equal to under root of kti, but kt is 16k and I is 4m. So if we simplify this, then we will get omega n is equal to under root of 4k by m. Then we will find out the damping factor zeta. So zeta is Ct divided by Cct. So Cct is the critical damping coefficient for the torsional system. So we can write this in terms of 2 under root of kti, because Cct is not known for this system. But for this value of kt, that is 16k, and value of I, that is 4m, is known. So we can write this in this value Cct in terms of 2 under root of kti, and we will put the value. So Ct is nothing but 9c. We will keep 2 as it is, under root of 16k into 4m. So if we simplify this, we will get 9c by 16 under root km. Now we have to find out the damped frequency, that is Fd. So Fd is equal to omega d divided by 2 pi. And what is this omega d? Omega d is equal to omega n under root of 1 minus zeta square. So value of omega n for this system is known. So I will underline this. And value of zeta for this system is known. So if we put the both values in this equation, then we will get the value of Fd, and this is the final equation to find out the frequency for the damped system.
Given question: for the system shown in diagram, establish the differential equation of motion. Find the value of damping coefficient for which the system is critically damped.
As per the question, we have to find out the differential equation of motion for this given system. Let us understand the given diagram. Mass m is pivoted about this point O. The distance of this mass m from O is L. On both sides of mass m, the spring with stiffness K and damper with damping coefficient C is connected, and the distance of both of this spring as well as damper is A from this point O. The system considered is critically damped system, and it is mentioned in the question. So for the critically damped system, we know that damping coefficient C is equal to critically damping coefficient Cc. So for this question, we have to consider this C is equal to Cc. Now to find out the differential equation of motion, we will consider this mass m is displaced through an angle theta about this point O. So we will draw here the diagram. So I will show here the displacement of this mass m. So this m is pivoted about point O. So here is the angular displacement. So we have to show this. So this is the final position of mass m. Here is the angle theta, and the direction of displacement is in the clockwise direction. Now when this mass m is displaced through an angle theta, then there is also the displacement for this spring as well as for this damper is x. So we will consider this displacement. This is the original position and this is the final position. So linear displacement we will consider as a x, and we have to show this in the diagram. Now we will consider the original point as a and this final point as a dash. Now if we observe this triangle OAA dash, now from this triangle we can say that x is equal to a into theta. So we can say that x is equal to a sin theta, but theta is very small, so sin theta is equal to theta. So we can write here x is equal to a theta. Now in the direction of this linear displacement, velocity is also in the same direction. So how we can write the velocity? So velocity is equal to x dot. So from this x is equal to a theta, we can say that x dot is equal to a theta dot. So we will get the value of x and x dot in terms of theta and theta dot. Now we will understand the different forces acting on the system. So when this mass m is displaced through an angle theta, then there is the accelerating torque develops in the same direction of the angular displacement, that is in the clockwise direction. So what is its value? So accelerating torque, we can also say accelerating couple is I theta double dot, where I is the mass moment of inertia of this mass m and theta double dot is the angular acceleration. So this is in the same direction of the angular displacement. Now we will understand the forces. So as the x is in the downward direction, so if we observe original position is A and final position is A dash, that is this linear displacement is taking place in the downward direction. So in the opposite direction, spring force and damper force will act. So this spring force, we will show the direction, that is in the upward direction, and we will say it as a Fs, and damper force we will say it as a Fd. Now these two forces will act in the upward direction. Now to balance this accelerating couple, we have to find out the external couple. So this external couple are due to these two external forces, that is due to these two forces, Fs spring force and Fd damper force. So how to find out this couple? So here point O is pivoted. So how to find out the couple and its a direction? So if we observe this Fs, we have to take this force multiplied by the perpendicular distance from this point O. So perpendicular distance from the point O is A. So how we can find out the couple? Couple due to Fs is Fs into A. So I will write here. And what is its a direction? So if I move the compass in the direction of Fs about this point O, then it is in the anti-clockwise direction. So this is the direction of Fs into A. Now in the same way for this Fd, how to find out couple? So couple is this force multiplied by perpendicular distance, that is Fd into A. So I will write here. So this is the couple. Now how to find out its a direction? So if I move the compass about this point O in the direction of Fd, that is in the upward direction, then it is anti-clockwise direction. Now if we observe this clockwise and anti-clockwise, both are in opposite direction. So for clockwise direction, if I consider positive sign, then for anti-clockwise direction we have to consider negative sign. Now we will write the two forces Fs and Fd in terms of theta. So Fs is equal to k into x. So x is equal to a theta. So we will write Fs is equal to k into a into theta. Now Fd, that is the damper force, is equal to c multiplied by x dot. But in this case, because this is the critically damped system, c is equal to cc. So we will write here cc into x dot, and x dot is equal to a theta dot. So we will write here cc a into theta dot, and we have to write the reason, that is this is the critically damped system. Now by Newton's second law of motion, we can say that accelerating couple I theta double dot is equal to summation of external couple, that is this is having positive sign, which is equal to minus Fs into A minus Fd into A. So if we multiply with these two forces with A, then it will become minus cc a square theta dot minus k a square theta dot, because a multiplied by a square we will write as it is. Now if we simplify this, then it will become I theta double dot plus cc a square theta dot plus k a square theta is equal to 0. Now what is this I? That is the mass moment of inertia of this m. Now this mass m is very small and it is pivoted about point O, and it is having the distance L. So I, for this mass m, we will write here I is equal to m into L square. So if we put the value, then this is the differential equation of motion for this system. So we will give here the equation number 1. So what is this differential equation? ml square theta double dot plus cc a square theta dot plus k a square theta is equal to 0. Now we will compare the differential equation of motion for this system with damped free vibration. Because if we observe this system, this is the spring, mass and damper system. But here the condition is given that this system is critically damped and the arrangement is different. Now if we observe this differential equation, that is the equation number 1, then it is in terms of theta, because here the angular displacement is taking place. So while comparing this equation with damped free vibration, we have to consider here the torsional system, because we know that there are two types, linear system and torsional system. But because this equation is in terms of theta, so we have to consider the damped free vibration equation in terms of theta only, and it is applicable for the torsional system. So what is this equation? That is I theta double dot plus ct theta dot plus kt theta is equal to 0. Now what is this ct? That is the damping coefficient for the torsional system, and here kt is the stiffness for the torsional system, or we can say stiffness for that shaft. So this is the equation number 2. Now if we compare this equation number 1 and equation number 2, both are equivalent to each other. So here coefficient of theta double dot, we can say that I is equal to ml square. Then if we compare coefficient of theta dot, then we can say that ct is equal to cc into a square. And if we compare the coefficient of theta, then we can say that kt is equal to k into a square. Now when we compare this, we have to find out the natural frequency as well as frequency for the damped system. So natural frequency omega n. So for the torsional system, we know that omega n is equal to under root of kt by I. Now we will take kt, that is under root of ka square by I, that is ml square. So for this system, this is the equation for the natural frequency. Now we will find out what is the value of zeta, that is the damping ratio. So for the torsional system, we know that zeta is equal to ct divided by cct. Now what is this ct? So ct is cc into a square. But what about the critical damping coefficient for the torsional system? So we have formula 2 under root of kti. So 2 under root of kt, that is ka square, and I, that is ml square. So if we simplify here, we will get 2al under root of km. So we have to put here. So again we will simplify here, a is getting cancelled. Now we will find out the omega d, that is the frequency for the damped system. So omega d is equal to omega n under root of 1 minus zeta square, and the frequency for the damped system fd is equal to omega d by 2 pi. So here 1 by 2 pi and value of omega d we will put. So instead of omega n, we will consider, for this system we have to consider this value. Now instead of this zeta, so zeta for this system, this is the value of zeta. So we have to use this. So when we put the value, then we will get the final equation for the natural frequency for the damped system.